Hello everybody. In this video we'll learn how to do some calculations with planes. In the previous video you learned how, given 3 points, let's say they're called P, Q, and R, you can calculate the equation of a plane. We learned 2 ways to do this, but we'll more commonly use the equation of a plane in this form: ax plus by plus cz equals d. As a brief recap on the steps involved, we first need to calculate the vector between 2 pairs of points. So for example, you could select vector v to be q minus p, the vector from p to q. Vector w could be r minus p, the vector from p to r. And then you would calculate the normal vector, or the vector perpendicular to the plane, using the cross product. So vector n would be equal to vector v cross vector w, and that uses the determinant notation we've learned about. And the components of that vector, a, b, c, give you the coefficients of x, y, z in the equation of a plane, and it's equal to a constant d on the right-hand side. You can calculate that constant by calculating the dot product of the normal vector with really any one of those 3 points. Here I have written n dot p, but you could calculate n dot q or n dot r if that's easier. Also in the last video, you learned, given a point, how you can check if it is on a plane. And the way you do that is, well, you plug the point into the equation of the plane and see if you get a true statement. If you do, you get something like 7 equals 7, then it is on the plane. If you get a false statement, then the point is not on the plane. However, if the point's not on a plane, you can do some more math. In particular, just like when we talked about calculations with points and lines, we could ask ourselves the question, what is the distance from the point to the plane? Also, if you're given different combinations of objects, you can ask different questions. For example, given the equation of a line, a parametric equation of a line, and an equation of a plane, do they intersect? And if they do intersect, then where and how do they intersect? With a line and a plane, there's actually a few possibilities. You could have the line lying above the plane and parallel to it, so maybe they don't intersect. You could have the line go through the plane at a single point, or you could even have the line completely contained within the plane. So there's 3 different possibilities to that question. Or, if you're given 2 planes, do they intersect? And if they do, well, where? Again, there's 3 possibilities. Either the planes could be parallel to each other, right? You could have one above the other, in which case they don't intersect. If they do intersect, right, they could intersect along a line, or one plane could literally be the same plane as the other. They could be 2 different equations which represent the same plane. So again, we've got a few possibilities there. I'd like to answer each of these questions. Once again, they build on the different vector techniques that we've learned throughout this part of the course. First, if you want to find the distance from a point A to a plane, I've represented as this green grid down here, it is very similar to finding the distance from a point to a line. It's a little bit easier actually. In this case, you first need to find any point which is on the plane. Call that point P. Maybe you're given the point, maybe you have to find one by picking some values for x, y, and z. Once you have a point on the plane, you want to calculate the vector v between those 2 points. So here v is a minus p. Now, the length of this vector is not the distance from the point to the plane, because this vector is probably not perpendicular to the plane. If you're interested in something perpendicular to the plane, well, thankfully we have the normal vector. Right? The normal vector are the coefficients a, b, c, lowercase a, b, c, of the x, y, z in your plane equation. What you would want to do is find the length of the projection of this vector onto this perpendicular. But the length of the projection is also called the component. So in order to find the distance from this point A to this plane, you want to find the component of the vector v on the vector n. And there's also a nice way to check. It's always nice to check your work. You can check just by recalculating with any other point on this plane. It's actually quicker to do an example than it is to explain it. So let's say we have the point A, which is equal to 1, 0, 2. And let's say we have a plane with this equation, 3x plus 4y plus 5z equals 2. So in that case, the normal vector is 3, 4, 5. It's these coefficients. So we need to pick any point which is on this plane. Maybe you can see some values for x, y, and z that work out nicely. If not, you can always just choose values for two of the variables and then solve to find out what the third must be to satisfy this equation. But one set of values which works pretty nicely is -1, 0, 1. That's a point on this plane. So you can calculate the vector from P to A. So calculate A minus P, and you get this vector, 2, 0, 1. Now to calculate the distance, we just need this component. And the formula for that is v dot n divided by the length of n. So in this case, see v dot n, we've got 2 times 3 is 6, plus 0 times 4 is 0, plus 1 times 5 is 5. Adding that up is 11, divided by the length of n, that's 11, divided by the square root of 50. And so that's our distance. And if you'd like to check your work, which I hope you do, you could choose another point which works out pretty nicely, even though it has a fraction, is 0, 1/2, 0. So again, finding that vector from P to A, in this case, it's the vector 1, -1/2, 2, and again, calculate the component with this new vector v. The vector n is the same as before, so you know you're going to have the same denominator. But here, we'd have 1 times 3 is 3, -1/2 times 4 is -2, and 2 times 5 is 10. Add those up, you get 11, and you get the same answer in both cases, so you can reasonably assume that you are correct. And that's how you calculate the distance from a point to a plane. But what if instead of a point in a plane, you're given a line in a plane? Well, in that case, we can try to find the intersection of those two. And here's how this works. Given the equation of a line, and we'll typically see this in the form vector m, slope vector m, times t, plus some base point p, we'd like to write the equations for x, y, and z all in terms of t. So do this scalar multiplication and addition, and then separate it out into 3 equations. Substitute those equations into the equation of the given plane, and try to solve for t. The number of solutions you get tells you the type of intersection. If there are no solutions, right, if you try to simplify and you get something crazy like 5 equals 13, then it's a false statement. There's 0 solutions, there's no intersection. Most commonly, you're going to find one solution. You'll be able to find one value for t, which means that the line and plane intersect at a point. It is possible, unlikely but possible, that you might get infinitely many solutions. Right? When you substitute into the plane equation, if all the values of t drop out, and you're left with something like 12 equals 12, well, that's true for all values of t. That means for all values of t, all the points on the line are on the plane. And in that case, the line is contained within the plane. So if you get 0 or infinitely many solutions, you know what the answer is and you can stop. But let's try an example where you get one intersection. So here's an equation of a line. Slope vector 1, 2, 1 times t plus base point 3, 0, 2. And here's an equation of your plane, 3x plus 4y plus 5z equals 2. Same plane as before. So separate out the equation of the line into the x, y, and z components. X is 1t plus 3, y is 2t plus 0, and z is 1t plus 2. Once you've got those, plug them in for x and y and z in the equation of the plane, and then we're going to do some algebra. So you get 3 times t plus 3 plus 4 times 2t plus 5 times t plus 2 equals 2. Distribute things through, combine like terms, solve for t. In this case, you'll get t equals negative 17 over 16. So that'll be kind of the time on the line at which you get an intersection. You can plug that value for t back into the line, and then you'll find out, or you could plug it into these equations for x, y, and z, and you'll find out the point at which they intersect. And as always, it's nice to check your work. And again, there's an easy check. Does this point really lie on the plane? You know it's on the line because when you plugged it into the equation of the line. You can check by plugging these values into the equation of the plane to see if they work. And if you simplify this through, probably the easiest way is to multiply both sides by 16 in this case to clear denominators. Then you're just left with whole numbers. You should see that you get 32 on both sides. So yes, the point is on the plane. And that's how you solve the second type of plane problem, the intersection of a line and a plane. The third kind of problem involves the equations of two planes. So how would you find the intersection of two planes? Well, it's really just a bunch of algebra. There are a bunch of steps. They're all simple, but there are a lot of steps, so we have to be very careful with our algebra. Let's say, in this case, we'll talk through the steps and do the algebra at the same time. Let's say we have these two equations of a plane, 3x plus 4y plus 5z equals 2, and 5x plus 3y plus 6z equals 7. The first step is to pick one of these equations of a plane and solve for one of the variables. You can use either equation, you can use any variable. Just in general, try to keep it simple. Right? The simpler you can make this, the better your life can be. So in this case, I took the first equation and I solved that for y. So I like working with quarters. So y is equal to this expression here. Next, with this equation you just found, plug it into the other plane equation and simplify as much as you can. And so in this case, since y is equal to this expression, I'll plug it in for y in this equation. I won't bore you by reading this out, but once you expand and simplify, you'll notice that the variable you substituted in for should be eliminated, and here we're left with 11x plus 9z equals 22. And I got that by clearing these denominators. It really can't get too much more simple. Now step 3, take this equation that you just got, solve it for one of the variables. In this case, I solved for x because, well, it's simpler, because 22 divided by 11 is just 2. So I liked solving for x because we got less fractions. Now, we're actually just about done. Whatever your innermost variable is, in other words, the variable that you have not solved for, let that equal t, and then write all the other variables in terms of t. Right, so in this case, I've solved for y in one place, and I've solved for x somewhere else. So this remaining variable z, I would let z equal t. And then I have x in terms of t, and I could plug those into the original first equation from step 1, then I could get y in terms of t. And to see how that looks in this example, right, here's the two equations I have to work with, the two variables we've solved for, and we'll let z equal t. Plugging that in up here, we have x is negative 9/11 t plus 2. Since I have both x and z in terms of t, I could plug those both in and write y in terms of t. This is a fair amount of algebra, but once you're done, here I got y equals negative 7/11 t minus 1. This is great. We're basically done. This is the last bit of hard algebra right here. Again, hopefully not too hard, just kind of long. Now we'd like to group terms, right? You should be able to get each one of these variables in the form of something times t plus something. Z equals t, you can write that as 1 times t plus 0. And now, well, your coefficients of t, those are the components of your slope vector, and the constants, that forms your base point. And that's it. That's how you find the line of intersection of two planes. And of course you want to check your work. The way you check your work is you should find one, maybe 2 points on this line and plug it into the equations of the planes to make sure they're on both the planes. One easy point is of course going to be your base point, and you can actually check if you plug 2, -1, 0 into both of those equations. And here's our original 2 equations of the plane. You'll find that you get a true equation in both cases. If you want to be even more confident of your answer, find one more point. In this case, I'd probably choose t equals 11 to generate another point, because that would cancel out a lot of these denominators. It's always good to check your work. And that's it. Those are the different types of calculations you can do involving equations of planes. That's it for this video. Thanks for watching.